Hello, my name is Vitor, and this is a presentation about our paper, Efficient Replication via Timestamp Stability. In our paper, we focus on planet-scale replicated systems. These systems are replicated in order to provide fault tolerance. So if a user is accessing a replica and this replica for some reason goes down, then the user can fail over to another replica and keep accessing the system. Now, these systems are replicated on a planet scale in order to provide low latency. By having replicas deployed all over the world, users can minimize the latency required to access the system. One question that comes up when we have multiple replicas of the same data is whether these replicas are consistent with each other. In this paper, we focus on strong consistency, and in particular, we consider systems that provide the gold standard, the linearizability. This, in a nutshell, means that the system behaves as if all commands are executed by a single thread, and so replication is transparent to users. And the way we're going to achieve this is with state machine replication, or SMR. In SMR, the system is defined by a deterministic state machine, and there is a protocol that determines the order in which commands are executed at each replica. One of the most famous SMR protocols is Paxos, which is leader-based. This means that when a client wants to submit a command to the system, it sends it to the leader replica. When the leader replica receives this command, it forwards it to f+1 acceptors, where f is the number of failures that we want to tolerate. So if we say that f equals 2, then the leader forwards the command to 3 acceptors, one being itself. Then, once these acceptors acknowledge the command, the leader can commit the command, execute it, and then send the result back to the client. So, what are the issues with this approach? Let's now consider that the client is located in Europe. Again, the command needs to be sent to the leader, but this time it needs to cross the Atlantic. After contacting the acceptors and executing the command, the leader sends the reply to the client, again crossing the Atlantic. If we compare this with a client located in North America, we can understand why leader-based protocols can be unfair to faraway clients. Moreover, the leader replica is doing most of the work and can, with enough load, become a bottleneck, so there's no load balancing. And finally, the leader replica is a single point of failure, since if it goes down, the system cannot serve requests until a new replica is elected as the leader. One aspect we haven't discussed about Paxos is how commands are ordered at each replica. In Paxos, the leader assigns the timestamp to each command, and then commands are executed in this timestamp order. So if a replica sees command W committed with timestamp 1, it can execute it right away. Similarly, if it sees command X committed with timestamp 2, it can also execute it as it has already executed the command with timestamp 1, command W. However, if it sees command Z committed with timestamp 4, it can't execute it until it receives the command committed with timestamp 3. Mencius is also an SMR protocol, but with multiple leaders. In Mencius, each leader commits commands in a similar fashion to Paxos, but commands are ordered differently. Since we can have commands committed with the same timestamp, we're going to break ties using the leader identifier. So in this example, we have 3 leaders, A, B, and C. If a replica sees command W by leader A committed with timestamp 1, it can execute it right away, as no command can be ordered before W. If the replica then sees command X by leader B, also committed with timestamp 1, it can also execute it as the command with timestamp 1 by leader A is already executed. However, if it sees command Z by leader A committed with timestamp 2, it can't execute it until it receives the command by leader C committed with timestamp 1. So while Matthew's approach is more fair than Paxos and provides load balancing, it runs at the speed of the slowest leader. And the root problem we have identified here is that a command's timestamp is computed by a single process. To sidestep all these issues, in this paper we propose Tempo, a leaderless protocol in which, instead of having a single process deciding the command's timestamp, we have a majority of processes proposing a timestamp for the commands. Then, the command's timestamp is the highest of these proposals. Again, we have an example, and command W is received by majority A and B, both proposing timestamp 1 for the command. Thus, command W is committed with timestamp 1. Command Y is then received by process A, which proposes timestamp 2, and process C, which proposes timestamp 1. Since the command's timestamp is the highest of the proposals, command Y is committed with timestamp 2. Finally, command X is received by majority B and C, both propose timestamp 2, and thus command X is committed with timestamp 2 as well. So this is how Tempo computes the timestamp of commands. After being committed with a timestamp, commands have to be executed. So now we need to know when it is safe to execute a committed command. For that, we resort to timestamp stability, which tells us that process I can only execute command C after its timestamp T is stable, and that is when every command with a timestamp equal or lower to T is also committed at process I. In the paper, we show that some timestamp T is stable at process I once process I knows all proposals up to T by some majority. If we go back to the previous example, when we see command W committed with timestamp 1, timestamp stability tells us that it is safe to execute command W if we have all proposals up to 1 by any majority. And indeed, we have all proposals up to 1 by majority A and B, and so command W can be executed. However, when command Y is committed with timestamp 2, this timestamp is not yet stable as we don't have all proposals up to 2 by some majority. Intuitively, it's not safe to execute command Y because another command can still be committed also with timestamp 2. This can occur when such command gets proposals from processes B and C, in which case it would be committed with timestamp 2. And this is exactly what happens with command X. Now, when we see these two commands committed, it is safe to execute them as timestamp 2 is now stable. And that's because we have all proposals up to 2 by some majority, for example, A and B. In this example, we have two commands committed with the same timestamp, Y and X. And when that happens, we break ties using their identifiers. So in this example, we execute first X and then Y. One of the main benefits of Tempo is that it provides low-tail latency in a predictable manner. In this experiment, we consider two settings. On the top, we deploy 256 clients per process, while in the bottom, we deploy 512. Here we compare Tempo with three other leaderless protocols, Epaxos, Atlas, and Caesar. We can see that these three leaderless protocols offer extremely high tail latencies that reach several seconds, making these protocols unusable. Moreover, doubling the number of clients almost doubles the 99.9 latency percentile. On the other hand, Tempo provides a 99.9 latency percentile of around 360 milliseconds, and this percentile is virtually not affected by the increased load. Besides performing well in practice, we prove in the paper that Tempo always ensures progress in a synchronous network. This is not the case of the three other leaderless protocols, since there are scenarios where these protocols don't even terminate. In the paper we show that Tempo can be easily extended to support partial replication scenarios. There we compare Tempo with EuroSys', a state-of-the-art protocol designed for partial replication. Our evaluation shows that Tempo can provide a throughput that far exceeds the one of EuroSys'. The paper also describes Tempo's fast path condition and its simple recovery mechanism. Finally, the paper contains some details about the evaluation framework that we have designed in order to implement and evaluate all these protocols. So, in summary, Tempo guarantees progress under a synchronous network without the need to contact all replicas, which was not the case in previous leaderless protocols. Tempo also provides predictable performance even in contented workloads. And finally, Tempo supports both full and partial replication scenarios, and in both, its timestamping and stability detection mechanisms are fully decentralized. Any questions, just reach out on Twitter or by email. Have a nice day.